Traditional screen film radiography, where a physical copy of an X-ray was chemically developed, is obsolete. Today, when incident radiation strikes a solid plane, the physical energy is instantly translated into a binary data matrix. The engineering problem governing this process is one of time. An X-ray photon is transient. For clinical data to be recorded, the high-energy state of that photon must be physically trapped to form a latent image before the energy naturally dissipates. Ultimately, digitizing that trapped energy requires an analog-to-digital converter, or ADC. But the ADC is entirely dependent on the physical hardware preceding it. The architecture of that initial capture point dictates the absolute limits of the system's resolution. To trap and translate radiation, modern clinical engineering relies on three distinct hardware architectures: computed radiography, indirect digital radiography, and direct digital radiography. Each employs a different mechanism of action. Computed radiography uses delayed light emission. Indirect DR uses instantaneous light emission. Direct DR generates electrical charge carriers. By analyzing the solid-state physics governing each of these pathways, we can map exactly how anatomical density is converted into data. Digital radiography comprises three distinct physical methodologies, each offering a different technical pathway for translating human anatomy into a permanent numerical grid. When X-ray energy hits a phosphor screen, it converts into light through X-ray luminescence. This happens via two mechanisms: fluorescence, which is the immediate emission of light, and phosphorescence, where the emission of light is significantly delayed. Computed radiography, or CR, relies strictly on phosphorescence. It exploits this delay to temporarily store energy in physical space. The medium for this trap is a 0.3 mm image plate embedded with a lattice of barium fluorohalide crystals. Latent image formation begins when a single X-ray photon is absorbed, ejecting a high-energy photoelectron and ionizing a track through surrounding atoms. That single track initiates a massive secondary reaction, releasing over 100 secondary electrons. These electrons become physically trapped at specific defect sites throughout the phosphor layer, holding the latent image in their physical positioning within the crystal structure. If left alone, these trapped electrons spontaneously relax, decaying the image. To extract data, a red laser beam scans the plate, knocking the electrons back to their ground state and forcing them to release stored energy as visible blue light. The released blue light is collected by optical fibers and fed into a photomultiplier tube. The tube amplifies the light, converts it into an electrical current, and sends it to the ADC to be digitized. Because the electrons have returned to their ground state, this readout process is destructive. The latent image is eliminated. Before the cassette can be used for the next patient, the plate is exposed to bright white light to erase any residual signal. CR successfully traps energy, but its reliance on a physical cassette and a mechanical optical readout step limits clinical throughput and introduces light scatter inefficiencies. Digital radiography, or DR, eliminates the cassette entirely. X-rays hit a permanently placed set of hardware that channels information directly to a readout mechanism. The first DR architecture is indirect DR. It achieves instantaneous data transfer, but it relies on a scintillator acting as an optical middleman. Below the X-ray window sits a 500 micrometer thick scintillator layer of cesium iodide. To prevent lateral light scattering, it is grown into a channeled needle-like crystal structure, forcing the generated light to travel straight down. The conversion rate is massive. The absorption of a single X-ray photon releases approximately 3,000 light photons in the green part of the spectrum. These green photons strike the active matrix, a rigid layer of readout electronics. Within this matrix, every individual pixel contains three discrete hardware components: a photodiode, a charge storage capacitor, and a thin film transistor, or TFT switch. To extract the image, these TFT switches open sequentially, row by row. They release the latent voltage stored in the capacitors into charge-sensitive amplifiers, digitizing the signal instantly. But the active matrix introduces a physical hardware constraint. The space taken up by the storage capacitor and the TFT switch cannot be used to detect light. The ratio of the light-sensitive area to the overall pixel footprint is known as the fill factor. This creates a direct engineering trade-off. While smaller pixels theoretically improve spatial resolution, the TFT circuitry cannot be shrunk at the same scale. As the pixel size decreases, the active photodiode area drops, reducing the detector's overall efficiency.
Indirect DR provides an immediate, cassette-free workflow, yet converting X-rays to light, paired with the fixed physical footprint of its circuitry, creates a necessary compromise between spatial resolution and detector efficiency. To bypass the unsharpness caused by optical scatter and improve efficiency, engineers developed direct digital radiography. This architecture solves the optical problem by removing the scintillator middleman. The capture material is replaced with an amorphous selenium photoconductor. When an X-ray photon hits, it converts directly into free electrical charge carriers, generating negative electrons and positive holes. To organize these charges, a surface electrode at a positive potential attracts and discards the negative electrons. The remaining positive charges are drawn straight down into the charge storage capacitors, instantly forming the latent image. Once the charge is held in the capacitor, the active matrix behaves exactly as it does in indirect DR. The TFT switches are gated sequentially to read the charge pattern and transfer the voltage to the amplifiers. By converting photons directly into electrical charge without an intermediate light phase, direct DR achieves the purest theoretical translation of incident radiation into digital data. Shifting from hardware architecture to the resulting digital file, medical physicists rely on strict mathematical functions to objectively measure how well these detectors perform. This chart graphs the modulation transfer function, or MTF. It plots spatial frequency against the MTF ratio, serving as the definitive measure of a detector's spatial resolution limits. An MTF of 1.0 means the spatial resolution recorded by the detector perfectly matches the object being imaged, but as the spatial frequency of the details increases, inherent system noise degrades the signal. The line curves downward until it reaches an MTF of 0, the limiting spatial resolution where no information is conveyed. While MTF tracks resolution, dose efficiency is measured by the detective quantum efficiency, or DQE. This formula calculates the ratio of the squared signal-to-noise ratio output against the input, defining how efficiently the detector uses the X-ray dose provided. For context, a standard computed radiography plate has a typical DQE of only 0.25. This means the detector successfully exploits just 1/4 of the incident X-ray photons. Because digital systems artificially adjust image brightness, radiologists lose the visual cues of overexposed physical film. Instead, system speed and incident dose are tracked numerically using the exposure index and the S number. The S number is calculated as 2000 divided by the incident dose. An S number under 200 yields an improved signal-to-noise ratio, but requires a higher radiation dose to the patient. MTF and DQE define the digital radiograph as a mathematically bound map, governed strictly by the quantifiable physical efficiency of the detector. Regardless of whether the system uses CR phosphors, indirect scintillators, or direct photoconductors, the raw voltage signal pulled from the hardware is inherently flawed. Solid-state arrays carry inherent hardware artifacts. The X-ray absorption layers exhibit non-uniform sensitivity across their surface, causing irregular shading. And within the millions of microcomponents in the active matrix, individual rows or columns of pixels will inevitably fail, creating dead spots in the data. Before human viewing, the system applies precise algorithmic corrections. To fix irregular shading, it applies a gain calibration mask, subtracting variations from a baseline reference map. To fix dead spots, it uses pixel calibration, mathematically interpolating the data values of functioning neighboring pixels to guess the exact value of the dead zone. Next, the software utilizes auto-ranging. By generating a histogram of the raw data, the software identifies and excludes extreme high and low values that contain zero clinical information. Finally, a lookup table, or LUT, executes grayscale modification. The raw binary data is systematically remapped to a new range of contrast values, matching the visual capabilities of a flat panel display monitor. The capture of a radiograph requires transient high-energy photons to be trapped through phosphorescence, optical scintillation, or direct electrical charge conversion. Once that physical energy is held in place, it is systematically routed through precise solid-state architecture, pulled through an analog-to-digital converter, and mathematically corrected into a functional array. Modern digital radiography replaces the chemical darkroom with crystalline traps, active matrices, and algorithmic processing to make the invisible permanent.